Good evening, everyone. Well, it's evening when I'm making this video anyway, and given that you're a bunch of teenagers, that half of you don't crawl out of bed till the evening to watch this anyway, so it's probably the best greeting. Now, left you for the last 2 weeks to just get on with that revision work. Hopefully you've done all those component 1 and component 2 papers by now, and hopefully you've also done, as I suggested, and saved the last one of each to do under exam conditions, marked them, graded them using the grade boundaries I sent, and sort of they've got a useful sort of grading point for you where you can see where you actually stand grade-wise at this stage of the biology course. Now, I should add, I know that quite a few of those past papers were really hard, especially the specimen in the 2016 papers. EduClass, the exam board we use, is notorious for setting really hard exam papers with some really obscure questions on them. If I sat one of those papers, I'd drop quite a few marks, I think. But don't worry too much about that. The grade boundaries are lowered accordingly, as you've probably seen. A's can often be got with anything from around 60 to 65% on those papers. But hopefully it's been some useful practice for you anyway to do all those exam papers. If you haven't finished them, by the way, don't panic about it. Although I'm going to start setting you some more work this week, next week it would have been the half-term week, so I won't set any further work for that. So as long as you get all the past papers done, plus the work I'm setting this week done over the next 2 weeks and do it by June the 1st, that will be fine. Talking of June the 1st, some of you might have been hearing rumours that college will possibly reopen then. It's only possibly, we're still awaiting final confirmation that we can reopen, and even if a certain amount of reopening is allowed, it's not as though we can have all classes back on full timetables with 15 to 20 people in a classroom. But we'll basically wait and see. We're awaiting further guidance next week, but I really hope that we can at least get some contact time with you. It will obviously be in small groups, and as I say, it won't be a full 5 hours a week, but we'll wait until next week and see what we can get. Anyway, this lesson is on the opening part of topic 1.5 on populations. Topic 1.5, why are we studying that? You might be thinking. Let's just quickly put it in context. This is a course guide I gave you right at the start of the academic year last September. So you can see in the first year you were due to do the core concepts, which we did in the first term, all of those topics. We've since then done the 2 component 2 topics, these 3 component 3 topics, and basically those 5 core topics plus these additional 5 topics make up the A1 course, or what used to be the AS level course. We're now starting with A2 work, but we tried to do a little bit of the A2 work in the end of year period at the end of the first year. As you can see, this topic's 1.5 and 1.6 we try to cover. Now 1.6 is really set for you to sort of self-teach over the summer holidays. So in this end of year period, it's topic 1.5 that we are covering. By coincidence, by the way, it's a strange little bit of symmetry with what we're doing in chemistry. For those of you who do both subjects, in chemistry we're doing topic 5.1 in the end of year period, biology 1.5. Hopefully that won't lead to any confusion. Right, I've sent you a copy of the checklist. Topic 1.5 is called populations. This little video, I'm just going to cover the first 3 learning aims on that. Right, I've also sent you a note sheet to complete. Hopefully you've already printed that off. If not, pause the video and print it off now, please, because you'll need it to sort of follow what I'm doing on the video here. Now, first thing we're learning about is a bacterial population growth curve. I'm showing this here. This is actually slide 12 of the PowerPoint that I sent you as well, and you can copy this onto the top of the note sheet, and you then got some blanks to fill in. Now, before I go any further, I should add that that type of population growth curve is not actually found in nature. It's found in laboratory conditions where a small number of bacteria would be introduced to a petri dish with loads of nutrient agar on it. So these bacteria have lots of food, more than enough food for them, and also, it's on natural conditions. There are no competitors, no predators, and but therefore their population can grow very quickly. However, there are also no real interactions with the wider environment, apart from a small amount of air being able to get in. They will need oxygen still, but there's no sort of renewing of their food supply and no removal of their toxic waste products here. And what you find, therefore, is you find their population grows in this pattern. At first you get the lag phase, which is sort of this bit and just the first tiny bit of the upward curve. The lag phase is where really there's little or no population growth. That's because a new colony of bacteria are introduced before they can start to reproduce. The individuals need to grow. Bacteria mostly reproduce by simple cell division, in other words, mitosis. But to carry that out, they need to replicate their DNA, synthesize enough protein to make the mitotic spindle, etc. And it all takes a bit of time. So whilst they're doing that, the population isn't really growing. Once they start reproducing, they very quickly grow in the log phase, then reach a stationary phase where the population reaches what's called its carrying capacity, which is the maximum number of individuals that that environment can sustain. Now, because this was an artificial situation, the bacteria population would then enter a death phase. You don't usually get this in natural situations, this death phase, but basically they will run out of food and too much of their own toxic waste products will accumulate and start poisoning them as well. So you get that. Right, I should add that if you've got a natural environment, this is the more typical pattern of population growth. If a small number of individuals of a species were introduced to a new environment, they'll still go through the lag phase, you'll still get the log phase. The stationary phase is then reached and they basically just stay at that level. It's not quite a fully constant level. You can see the slight fluctuations. And this is what we would find in a natural situation, not only for bacteria, but for animals, plants as well, will usually follow this type of pattern. If you're talking about animals in the lag phase, it's not so much just that they need time to replicate their DNA and produce more protein. Well, they do have to do that. But with animals, of course, it's a much longer lag phase. For bacteria, it might only be 20 to 30 minutes in the lag phase. For animals, it could be months, even years. You have to wait for them to reach sexual maturity, find mates, etc., to start reproducing. This is the more natural population growth curve, but the one that you should have done on the handout is the previous one that included the death phase. Right, this point, I want you to pause the video and complete the first section of that note sheet on the population growth curve. Use the PowerPoint slides that I've directed you to on the email. Once you've done that, I would then like you to complete sheet 1.5.1, which I've also attached to the email. Again, use the PowerPoint slides to help you complete that sheet. Come back to me only when you've done those two things, please. Right, I've got sheet 1.5.1 up here as well. Hopefully you've done all that. You can check your answers as well. And I should add that whilst all of these terms are useful terms to understand, there are only 2 of them that you actually have to recall word for word definitions of. Those are the ones on the note sheet, population and carrying capacity. So do copy those 2 definitions over at this point. Pause the video again if you need to and just get that done quickly. Right, moving on again. Just one last thing to look at for today, and that is the factors affecting the sizes of populations. Now, there are quite a few obvious factors that affect population sizes. Availability of food is often the most important one of all, but there are other things: temperature, rainfall, competition, etc. all can play a part. Now, the factors which affect population sizes can be split into 2 types. One type called density-dependent factors, and these density-dependent factors actually sort of have a bigger effect if the population size is large, but they don't have much effect on small populations, as shown there. Density-dependent factors are also often called biotic factors because they are basically connected with other living organisms. The main density-dependent factors: competition, availability of food, also disease. Diseases spread far more rapidly in dense populations. Obviously, the more individuals of an organism, of a species you've got in one area, the more they're competing with each other for competing with each other for food. Now, the second type of factor are called density independent factors, which means basically they have the same effect on a population, whether there's huge numbers of individuals there or whether there's only small numbers of individuals. And these are often also called abiotic factors because they're not directly connected to other living organisms. Now, a classic one is temperature. If the temperature in an area suddenly plummets to 0 degrees, it's going to wipe out all the organisms of most species. And that will happen regardless of whether there were thousands of organisms present or whether there was only 5 or 6 organisms present. They still all get wiped out due to a sudden plunge in temperature, whereas that would not happen in food. If you've got a sudden decrease in the amount of food available, if the population numbered 1,000 individuals, that would really decimate the population. But if there are only 5 or 6 individuals per species there and the amount of food rapidly decreases, well, it wouldn't really matter. There would still be enough for 5 or 6 individuals. So that's why sort of food availability is a density dependent factor, but temperature is a density independent factor. Right, that's about it for today. Nice short video really. All I want you to now do is quickly fill in the top part of page 2 on the notes. And once you've done that, do the other 2 things which I've mentioned in the email anyway. Complete sheet 1.5.11 and then go on and do section A on the question sheet that I set you. You can mark all of that for yourselves. I've also attached a mark scheme for all of this. Right, that should be enough work to keep you going for a couple of days at least. I'll be in touch again later in the week to set more. Okay, hope you're all well, all the best. Hopefully might be able to actually catch up with you in person sometime during June. It would be really good if we could. Okay, all the best everyone, bye now.